Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Daniel Holz, who is a professor of physics, astronomy, and astrophysics at the University of Chicago, the Enrico Fermi Institute, and the Kavli Institute for Cosmological Physics. His research focuses on general relativity in the context of astrophysics and cosmology. He's a member of the Laser Interferometer Gravitational-Wave Observatory, LIGO, collaboration, and was part of the team that announced the first detection of gravitational waves in early 2016 and the first multi-messenger detection of a binary neutron star in 2017. Welcome, Daniel.
Thanks for having me.
Yeah, thanks for doing this. So I have a few of your papers here, Daniel, but before we get into it, I want to set the context for LIGO, something that you have done a lot of work in. People are generally familiar with. They would have at least heard the term LIGO. Would love to get sort of a little bit of a design detail of how that all came about. It's an engineering marvel, 4 kilometers long tunnels, I believe, and we are trying to measure the the diameter of an atom or something like that, something extremely small amount in such large distance. So could you talk a bit about the machinery itself of LIGO?
Sure. Yeah, and LIGO really is this remarkable, machine, this instrument. I call it the most sensitive instrument, ever built, and I try to give a sense of, why that is.
Yeah.
But I think, before we get into that, it's probably useful to have a sense of gravitational waves, which is what we're detecting,
right,
and what they do, so that we can understand what LIGO is doing.
Yeah.
And so, the goal here is to detect gravitational waves, and we can talk a lot more about, what they're about and how they arise out of the theory. But the very short version of gravitational waves is that they're ripples in the fabric of space-time itself. And so just like you have waves on the surface of the ocean, or you have sort of, oscillations in air, those are sound waves.
Yeah.
You can have waves in space and time.
Right.
And those are caused whenever objects move. And so if you wave your hand to say bye to someone, waving your hand creates these oscillations in space and time, in space-time itself.
Right.
And so the way I usually describe it is, these gravitational waves are the way the universe keeps track of where everything is. So as everything moves around, it sends out, every object sends out waves, and those waves tell the rest of the universe that this object has moved.
Yeah, that's conceptually very interesting. So anything that moves is essentially using gravitational waves to communicate with the rest of the universe, is the way to think about it.
Yeah, that's right. And so you can think about it as what gravity, we all have gravity. If we have mass, we kind of are pulling through the gravitational force everything around us, just like the earth pulls us down, or if there's an apple on a tree and it comes detached, it'll fall to the surface of the earth. That's the gravity of the earth pulling.
Right.
Everything has gravity. We have gravity. The sun has gravity, and it's what keeps the earth going around in a circle. Everything has gravity. Now, when an object moves, the gravity in some sense has to be updated. When I move around, if I go across the room, then the most distant galaxy needs to know that I've moved a little bit, and so it has to update the gravity. I'm now pulling from a slightly different direction, and the rest of the universe needs to know that. And the way I communicate that is by emitting gravitational waves, which go at the speed of light to the distant reaches of the universe to update the entire universe that I've moved.
Yeah, so in that context, Daniel, it's not like sound waves. It's not really like the wave in the ocean. It's really I don't know how to how to think about this. It's really the space-time itself doing that, right? So it's not something that we can observe in any
That's right.
way, right? Yeah.
That's right. So, Gil, that's exactly the point. So here what happens is, okay, there are these oscillations in space-time, but what do they actually do? Well, what they do is they cause distances to change.
Yeah.
And so if you imagine, you have two walls or the opposite walls in a room, as a gravitational wave comes through, it causes the distance across the room between the two walls to change, to oscillate. Now, you might look around and say, well, that's obviously not happening. The walls of the room are pretty stationary.
Right.
My claim would be, oh, no, it is definitely happening. It's happening all the time, but the effect is very small. And this is where it starts to sound like science fiction. And this is why, I should say, Einstein, of course, he wrote down the theory of general relativity, or theory of gravity, over 100 years ago in 1915. And there were a bunch of predictions from that theory, one of which was the existence of black holes, and another of which was the existence of gravitational waves. But at the time, he said, and many people thought, that we would never detect gravitational waves. And it's for the following reason. Okay, now let's consider a very strong set of gravitational waves passing through the Earth right now. Okay? Right. Very strong waves. So what we want to do is get some sense of how much are the walls, what's this change in distance that we're talking about? And it's very hard to think about. So I'm going to give one example, which may or may not be helpful, which is, let's imagine we're observing the nearest star, not our sun, but the next nearest star. Okay, so that's
a few light years away.
Exactly, 4 light years away or so.
Yeah.
So that means at the speed of light, it takes you 4 years to get there.
Right.
And just for reference, to get to the sun takes you 8 minutes.
Right.
4 years is a long time. Speed of light is very fast, so this is pretty far. I mean, it's the nearest star, but it's still pretty far.
Yeah.
Okay. So now you have to think, okay, there is that star. It's way out there, 4 light years away. Okay. Now, here comes the strong gravitational waves. They're passing through now. And so the distance to that distant star is changing. The amount it changes by for a really strong gravitational wave is about the width of a human hair. Okay.
Right.
So that star, the distance to that star is vibrating. It's coming closer and farther away and closer and farther away by about the width of a human hair.
Yeah.
And that's what we want to be able to measure effectively. We're trying to measure those sorts of fractional distances.
Yeah.
And so when you think of it that way, at least to my mind, as a physicist, as being trained and all, it's obviously impossible. That's such an extreme measurement. How could anyone do it?
Right.
And that's what sets the stage for LIGO.
Yeah, and so you unleash engineers, and they can make things happen. just to set the context again. So this is also symptomatic of the fact that gravity is a very weak force of the four fundamental forces that we know, right? It's so weak, it's really difficult to really measure it. I mean, here we are measuring the changes in it. We can definitely measure
Yes.
gravity, but measuring changes
Yes.
in gravity is an extremely difficult task.
That's exactly right. And so it's the weakest force by a long shot, which is why, you can think of it as the entire Earth is, right now pulling on me, trying to pull me down to the surface of the Earth.
Yeah.
And I'm sitting on a very flimsy chair.
Right.
And that flimsy chair can overcome the entire gravitational force of the Earth.
Right.
And that's a sign of this difference in the forces. And it should be said, that's why these effects are so tiny and so hard to measure.
Yeah.
But because these effects are so weak, it also says that this is an incredibly powerful way to learn about the universe. Because once these waves are emitted, nothing interferes with them.
Right.
Because nothing, gravity is so weak that it's not like you can build up a wall and block these waves from going through. The waves go right through the wall, right through the Earth. They basically traverse the entire universe and don't change at all. You get a perfect representation of them. And so by measuring them, we get a very clear, picture of what created them in the first place. It makes them very powerful.
Right. Yeah, I want to ask you a quick question, Daniel. I don't know if this is relevant. So once the gravitational waves are formed, like you say, it's going to go on to the end of the universe. Could we at any point detect some? So if there is an end to the universe, will they get reflected back?
Right. So there are different ways to answer that.
Yeah.
So I think, in the picture in your mind, you probably have the idea that there's an edge. Right. And then if that is somehow a reflective boundary, they might reflect off of that.
Yeah.
Most models of the universe don't produce edges, but there is one very clear edge to the universe.
Yeah.
And that's an edge, if you like, in time. It's also in space. It's called the Big Bang.
Right.
And so you can think of it as that was a very distinct feature. And at the Big Bang, or tiny fractions of a second after the Big Bang, we do think that gravitational waves were emitted, and that there would be a whole spectrum of gravitational waves created at that moment.
Right.
And that's called the stochastic background, the cosmological stochastic background. And that's one of the holy grails of the field, would be to detect them. And so that's something that we're very excited about. And it's exactly one way to think about it, just as you described. It's this moment where the whole universe came into being, and from that point on, the waves would just continue to propagate through the universe, and they should be out there today, passing through us right now. Right. But they're even less, they're if you like, we usually use analogies to sound, and they're not nearly as loud as the loud ones we were talking about, which create these tiny effects on these distant stars.
Okay.
So those are even harder to detect, and we haven't detected them yet.
Right. And so the fact that they are really difficult to detect did not discourage the engineers. So how exactly did the engineers go about constructing LIGO? What exactly is the machine? Yeah.
Right. So, and that's exactly right. I mean, there were a few intrepid souls that, first of all, proposed that this could be done, and then worked on it for decades. And eventually, the story, succeeded, but it really took, extreme perseverance. And, in some sense, you could say they're kind of foolhardy, because all the indications were that this was impossible, but they somehow just kept going. So the basic idea is pretty simple. It's called an interferometer. And this technique was really pioneered by Albert Michelson, who happened to be the first department chair at the University of Chicago. And what he did was he built the following thing. He he built an instrument where light would go down two separate perpendicular tunnels, if you like. So imagine you put your arms out at 90 degrees, so in an L, and you have your arms out, and what you do is you just ask if light goes down one arm, bounces off the tips of your fingers and comes back, and light goes down the other arm, bounces off the tips of the other hand and comes back. Which path takes longer? And what Michelson originally was trying to do was show that the speed of light changes in different directions depending on the motion of the Earth, because everyone knew that light must go through a material like the ether. And so that's what Michelson was interested in. He showed that actually light always goes at the same speed. It always goes at the speed of light. And that was a major discovery. He won the Nobel Prize for that. And that actually helped usher in the theory of special relativity and general relativity, and the theory that in the end predicts black holes and gravitational waves and everything else. So that's kind of the origin of this instrument, and it's a very simple instrument. You just shoot light down two tubes, and you ask how long does it take, and you compare, and you kind of race the light down the two tubes. So we're doing the same thing.
So just a quick one, Daniel. So so light is going in one direction. So we are measuring the reflection back. Is that how it's done?
Yes.
Okay.
That's right. So you can think of it as, now what we've done is we have, same thing. It's two tubes. Now they're 2.5 miles long, each of them. So 4 kilometers long. And then at the end is a very, very shiny mirror. And it's sort of the world's shiniest mirror. It's a really, really state-of-the-art shiny surface, very carefully controlled. And then we have a state-of-the-art laser, very, very stable. And what we do is we take the laser and we split it into two beams, and we shoot the light down the two arms, and it goes all the way down, comes back, and then we compare the arrival time. We compare how long it takes to go down the two arms. And if one arm gets slightly longer than the other, then the light takes slightly longer to go down and back.
Right.
And we can measure that. And that's what we're doing.
So the idea here is that if a powerful gravity wave comes through where these tunnels are, in whatever direction it comes through, it will have an asymmetric effect, right, on the two arms, the two tunnels that are perpendicular. So if you detect a change in sort of their length, so to speak, by this technique, then we could conclude that there is some sort of a gravitational wave moving through. There are multiple things like this, right? This is one in Louisiana and one in Washington, something like that.
That's right. And there's also one now in Pisa, Italy, just outside of Pisa, called Virgo. The ones in Washington State and Louisiana, those are the LIGOs, and that's the U.S. Instruments funded by the National Science Foundation. Then there's a European one, and now there's one being commissioned in Japan called Kagra, and there's one in the kind of advanced planning stages in India called LIGO India. So there's a whole network of these.
And the reason for the multiple things is that when we detect something, we want to detect that at multiple locations to assure that it's not some local disturbance, is it?
Yeah. So there are two reasons. The one you just described is probably the most important, which is, as we described earlier, it's so extreme. The sensitivity of these instruments is so extreme that if you have waves crashing on the shore hundreds of miles away, that causes vibrations which can mess you up. If a truck is driving by anywhere nearby, that causes all sorts of vibrations which mess you up. The wind blowing over the building can be a complete nightmare. Any source of noise has to be controlled for, understood. The Earth is always shaking. Of course, there are big earthquakes, but there are also tiny, tiny little earthquakes all the time. and that causes noise, which is very hard to compensate for. So all these things have to be taken care of. So when a real gravitational wave passes through, what it'll do is it'll pass through the entire Earth, and all detectors should register it. And so what we can do is have two of them, and really they should see the same gravitational wave at basically the same time. And if that happens, you can be fairly confident it's real, and it's not that someone dropped a wrench somewhere in the tube and that caused what you detected.
Yeah, so they have to be simultaneous, and they have to be, I guess the measurements have to sort of sync also, right, to reach the conclusion.
The measurements have to...
Measurements meaning whatever we measure in Louisiana should be the same in Italy as well.
Yes, that's right. That's right. And so not only do they have to agree, but they also, preferentially, we would hope, at least right now, that they agree with our theory. So our theory makes very clear predictions. This is what, like, say, two black holes colliding should sound like in gravitational waves. And then we can look at our data, and if we have something that looks just like that in 2 or 3 of our detectors, then we have very high confidence that this is real and it's not some source of noise.
Yeah, one thing that puzzles me, Daniel, is I don't know anything about this. So what is the sort of the frequency of black hole collisions in the universe? Are they rare enough? But my initial thinking was that they should be going on all over the place at all the time. That, how would we actually measure a specific instance?
Yes. Okay. So the short answer to that is until 2015, we didn't really know.
Yeah.
And we had no way of knowing how often black holes would collide.
Right.
That's something that we've only figured out, because we're now, if you like, listening to the universe and hearing these black holes collide in gravitational waves. And now we can tell you how often, that happens. We have estimates for that. So the detectors that we have are sensitive only out to some smaller part of the universe. We can't detect black holes all the way to the very edge. And in the volume that we're sensitive to, the rate of detection is, roughly speaking, something like once a week.
That's all. Okay.
So once a week in this, in our kind of nearby part of the universe, 2 black holes collide and emit gravitational waves. When we then extrapolate to the... So here, nearby means something like the unit we use is megaparsecs, which is a million parsecs.
Right.
And each parsec is, on the order of a few light years. Yeah. So this is, so 1 megaparsec is a few million, say 3 million light years away. And we're talking about hundreds to thousands of megaparsecs. So billions of light years away. Exactly, billions of light years away. Which that's pretty far. But the universe is maybe something like 10 times bigger than that.
Right.
And so we're seeing a small fraction. And so when you kind of add up everything, our estimate is that every few minutes, somewhere in our observable universe, black holes are colliding. And as we get more sensitive, we'll see more and more of them.
Yeah, so the volume that you are looking at is about 1/10 the volume of the universe. And within there, you're seeing about one every week or so. So by extrapolation, we could,
Yes, it's not. So it's the distance is 1/10. So the volume is actually 1/1000.
Ah, right. Okay.
So that's how you go from 1 per week to a much shorter time scale. But yes, it's exactly what the extrapolation is exactly what you were describing.
1 per week. So it's also, are you also tuning these instruments to look for, sort of some specific mass, the mass of the black hole?
Yes. So that's a very important point. So we're we are sensitive in a certain frequency regime.
Right.
And so you can think of it as, when we listen, we only hear certain sounds, and we can't hear sounds that are higher pitched or lower pitched. There's just, kind of our audible range. And in this case, we're sensitive with LIGO, sort of by design, we're sensitive to objects which range from about the mass of our sun, so black holes that are roughly the mass of our sun, to black holes which are maybe 100 times the mass of our sun. Okay, that's our sensitivity range. We think that there are black holes that are much, much more massive than that, and those should also be colliding. We don't hear those at all. Those just go right through our instrument.
Yeah, I mean, it's a bit like tuning your shortwave radio to some frequency, right? So you have not one station, but a small range of stations you're listening to. So one solar mass to 100 solar masses. So what would be the frequency of the waves from that cohort?
Yeah, and this is why we use the analogy with sound. So the frequencies that we measure are comparable to the audible range of frequencies. So the lowest frequency waves we measure are on the order of 10 to 100 hertz. And then the highest frequencies are, in the kilohertz, so thousands of hertz. And this directly ties by frequency here. What we really mean is you have to imagine you have two black holes, for example, orbiting each other, spiraling in, just like the Earth goes around the sun. Now you have two black holes going around each other because of gravity. And the frequencies we're talking about is how long it takes them to go around. So for the Earth going around the sun, that's 1 year. But for the objects, for two black holes, as they get close, that happens much, much faster. And it happens in maybe 100th of a second. And so then, the frequency that we would observe those in gravitational waves, hear them in gravitational waves, is, hundreds of hertz or kilohertz. And so that's the connection. As they get more massive, that frequency actually goes down. So for smaller black holes, they go around faster and faster before they collide. For bigger black holes, they go slower and slower. But then when they collide, it's kind of at the bottom range of our sensitivity.
Right. Daniel, we will take a quick break. When we come back, we talk about some of the measurements you have taken and what. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. And so we are back. So Daniel, we are talking about gravitational waves and LIGO, the Laser Interferometer Gravitational Wave Observatory. And gravitational waves is really disturbances in space-time that happen when really heavy objects merge, collide, and so on. For example, two black holes colliding could create gravitational waves, but measuring them is really difficult because the real measurements you have to take is extremely small. But we have been successful in doing so with this machinery called LIGO that you have been involved with for many years now. And you are part of the team that announced sort of the first detection of gravitational waves. I think it was in early 2016, was it?
Yeah, that's right.
And so this is, so from that observation, we could back compute sort of the mass of the objects and what they might have been?
Yeah. So what we do is the event actually happened in 2015. Yeah. And it took us a while for us to analyze the data and be confident because, again, it's so extreme. really sure, double check, triple check
Right.
that we were really achieving, detecting something that's so minuscule,
Yeah.
just mind-blowingly minuscule. But we convinced ourselves, and we convinced the community, and published the papers. Um, and what we did is we, detected something in both our detectors.
Yeah.
So this is the Hanford detector in Washington and the Livingston detector in Louisiana,
Yeah.
and the signals were very similar. And then what we did is we carefully analyzed the kind of sound, the vibration that we got from the gravitational waves.
Mm.
And there's a very distinct sound. If you take the gravitational waves, just the frequency and the way that frequency evolves, if you take that and you just put it into your speakers, you get a very distinct chirp.
Mm.
It goes something like this. It just goes whoop, just
Mm.
like that.
Yeah.
It starts out at low frequency and chirps up to higher frequency and gets louder and louder, and then suddenly cuts off.
Right.
And by carefully analyzing that, how it evolves with time, where it cuts off, what node is it making when it cuts off, and comparing between the different detectors, that allowed us to figure out, so what we detected was two black holes. Each of the black holes was roughly 30 times the mass of our sun. So you're taking 30 of our suns and squeezing them down into a black hole that's a couple 100 miles across.
Mm.
And we have two of those, and then they were circling each other and colliding at about half the speed of light. This was all happening, on the order of 1 billion light years away, and that's what we did.
Yeah, it's again mind-boggling to think about it. So the event happened about 1 billion years ago, and we have been around on Earth only about 50,000 years. Technological innovation maybe last 100 years, and the creation of LIGO maybe last 10, 15, 20 years. And we were right here to catch that when it passed,
Yes,
when it passed the Earth,
right.
right? Yeah,
Yeah, and then it continues on to the far reaches of the universe at the speed of light, and we'll never detect those waves again.
right.
But so that sounds like we were extremely lucky.
Yeah,
And I mean, we certainly were in many ways. I mean, we detected these 2 days after we turned on, which was, very, we had worked on this machine. People had invested for decades. We turn on, and then 2 days later, we got an incredibly loud, kind of perfect signal.
mm.
And that's not the way things usually work. Usually you get a bunch of noise, and then but this case, it was really beautiful. However, what is actually happening is these, and we talked about this a little bit, these events are happening throughout the universe all the time.
Right.
And so, yes, any particular one, it's unlikely to detect it. But the idea that, when you turn on, you're going to start detecting gravitational waves from black holes colliding, that's something that should happen, with reasonable frequency. And that's exactly what happened in this case.
Mm. And so we got the same. What was the Italian facility on at that time?
It was not. So back
It
in
was not. Okay.
2015, when we
Yeah.
first turned on, they were not operating yet. So they didn't really start operating until a couple of years later.
Okay.
And
And
so they joined the network, and now, we routinely have 3 detectors operating.
so right now the status quo is you're finding these types of events once a week.
Yeah, on the order of once a week. I should mention, at this very moment, we're off.
Yeah.
We observed until about April, and then in part because of the pandemic, and in part because we were eager to kind of improve our sensitivity, we shut down, and we're off right now, and we hope to resume detections in just over a year. And so we'll turn back on then, and then we should be even more sensitive, and we should detect even more, sources throughout the universe.
Improving sensitivity. So you mentioned the thickness of a human hair a few million light years away. So what is the measurement we are taking at LIGO? What's the difference that we will see?
So right now, what we're sensitive to is on the order of, so the units we use are, fractional distances of on the order of 1 part in 10 to the 21. So
Okay.
that's, 0.000, 20 zeros, and then a 1. And
Yeah.
that will improve. We hope to improve our sensitivity so that it's roughly a factor of 2 more sensitive, or maybe a factor of 3 more sensitive. It depends on exactly where you are in frequency, and that makes a huge difference because it means we see, we detect sources that are that factor farther away, and then that means there's even more volume, and we detect even more of them. So
And
even
so,
small
yeah,
changes make a big difference.
right. And so when did the construction start?
So the initial construction, the sort of prototypes started in the 70s,
In the
1970s,
70s.
and
Yeah.
then it started in earnest on LIGO sometime in the 80s, and really got going in the 90s and 2000, and then got to a fairly robust state where you could start taking data. It wasn't that sensitive, but it was still interesting data in the late 2000, 2005 to 2010, and then there were a bunch of upgrades, and it got to sort of what we would think sensitivity finally in 2015.
Okay.
So you can think of it
Mm.
as it was a kind of 30 to 40 year you know ordeal. And I should say, even before that, people were working on detectors, other technologies such as bar detectors, where you have a giant piece of metal, and
Mm.
as the gravitational waves pass through, that piece of metal will kind of vibrate, and you
Mm.
can try to measure those vibrations. And people have been working on that technology for decades. um, it's been a very long process to get to the point where now we're finally routinely detecting them.
Yeah, I mean, the team should have had great belief, because if you just think about the technology, how that has developed last 40 years, to set off on this idea to have accuracies in the range of 10 to the power minus 20 in the 70s and 80s is just an incredible thing.
Absolutely. And just to be clear, I mean, there were a few individuals who really pushed this forward. Um, for example, Ray Weiss and Kip Thorne are often mentioned, and they won the Nobel Prize for this, and really played a crucial role, because early on they were saying, we can do it. Let's try.
Yeah.
And then the National Science Foundation, they convinced the National Science Foundation. The National Science Foundation took huge risks
Mm.
and said, okay, we'll give it a shot. And you have to understand that in the community, there were many people, physicists, astronomers, that said, this will never work. It's a waste of money.
Yeah.
It's impossible to do. And we shouldn't even try. And it really, it's hard to kind of overstate how brave these
Mm.
individuals were to, commit their careers,
Mm.
spend so many decades building on something which, when they started, was clearly impossible.
Right,
And
right.
then what happened was technology kind of caught up, lasers caught up, and our ability to fabricate mirrors caught up, and our computational, I mean, we couldn't have analyzed the data the way we do. It would have been inconceivable when they started. But
Mm.
now computational power is so advanced that we can do the computations necessary. We couldn't even simulate the signals. We didn't even know what we were looking for
Mm.
until 2005, because it took that long for the supercomputers to get to the point where they could calculate what happens when two black holes collide. So much had to happen, and yet it all fell into place, so that on 2015, it was September 14th, 2015, when the waves swept through our detector. We were ready, and we detected them. We recognized them for what they were, and were able to, detect and make the announcement.
Yeah.
Um, and here we are.
Yeah, there is also, you didn't know the frequency, you didn't know the time either. So if the situation were that the frequency is a lot higher, meaning it's not once a week, it's once every 10 seconds, then it would not have worked either, right?
Well, if it had been much, so if the frequency of occurrence had been higher,
Yeah.
we still would have detected them.
Okay.
Um, because we would have just be detecting them much more often. If they're too frequent, there is a point at which they become incoherent and just become noise if
Right.
they're happening too often.
Right.
But that would have to be maybe 1,000 a second, and if that were, then would be overwhelmed. But we're pretty far from that. Now,
Right.
if they only happen once every few years,
Yeah.
we might still be waiting to detect one.
That's right. That's right.
And
Yeah.
a lot of people thought that could easily be the case because we didn't really know.
Right.
Until we detected it, we had no idea how often they were happening in the universe.
Yeah. So once a week is a sort of the right timing actually for the
Yeah,
experiment to
that's
work.
right. That's
And
exactly right.
yeah.
And that's part of that is luck.
Right.
I mean, we specifically built the instrument hoping that this was the case, but you don't know until you turn it on.
Yeah.
And
And so,
fortunately, we're
yeah.
right in the regime where we get to detect them.
Yeah. And so since you got a lot of data last few years, so what exactly are we finding cross-sectionally? If we look at the distribution of the masses of the stars, are they agreeing with our expectations, or are they showing data that may not be quite in agreement with the theory?
Yeah, so I would say both of those things.
Yeah.
So at this point, and a few weeks ago, we announced our latest catalog. This is kind of the sum total of everything we've detected through what we call the first half. So O3A.
Yeah.
So that's kind of the state of the art up until today, and that's a total of 50 events.
Yeah.
And you can now look at those, and the broad distribution of those events is more or less as we expected. We thought, there'd probably be some smaller binary systems down to, maybe 5 times the mass of the sun,
Yeah.
all the way up to really big ones, maybe 40 or 50 times the mass of the sun. We kind of expect to cross that range, and then we expected some binary neutron stars, and we've gotten at least 2 of those. And then there might be these neutron star binaries where we have 1 neutron star and 1 black hole together, a neutron star black hole binary, and we might have seen some of those. So all of that is kind of, more or less the sort of system we expect, and that's, very gratifying. Kind of the theory and the observations are in sync. However, certainly some of the things in the details look very odd. It just doesn't quite fit.
Yeah.
And so, for example, like we've detected some things which are unusually loud. And in that sense, so actually, let me just say it differently: unusually massive.
Massive. Yeah.
And so we've detected. For example, there was this recent event we announced, which was GW 190521, which was composed of a black hole that we think is about 85 times the mass of the sun, with another black hole that's about 60 times the mass of the sun. And those are big by our standards. Right. And in fact, they're so big that from what we understand from theory, those black holes should not exist. Theory says, we think we know how black holes are made. They're made by stars exploding and collapsing and forming black holes in supernovae. So stars at the end of their lives, and we can talk more about this, but stars at the end of their lives, when they run out of the nuclear fuel that they're burning to glow, when they run out of that, they burn all their fuel, they then collapse.
Right.
And then many stars actually explode because as they collapse, there's a bunch of astrophysics that happens that causes them to kind of bounce off themselves and explode. And what's often left behind is a black hole. And so that story works extremely well and says you can make smaller black holes and bigger black holes. But that theory says pretty clearly that you can't make black holes between about 50 times the mass of the sun and 120 times the mass of the sun, because there's this special physics effect called the pair instability, which just means you can suddenly make electrons and positrons, and that causes the star to explode without making a black hole. So theory says that you shouldn't get these big black holes, and yet we detected a binary system which looks like it's made out of two black holes right in this gap, and that's been a real surprise. For example.
So, so they are supermassive black holes, right? I mean, many millions of masses of suns at the center of galaxies.
Yes.
And so
exactly. Yes.
So those things are, so the gap that you're talking about is sort of a precise gap between 50 solar masses to 125 solar masses. And the physics that disallows that does not create any issues for that really huge black holes.
Yeah, Gil. So that is the sort of question that we're really. So you're absolutely right. When I'm talking about a kind of stellar mass black hole, so roughly the mass of our sun, maybe 100 times the mass of our sun, but in that range. Yeah. There are also supermassive black holes, including one at the center of our galaxy, and that's the Nobel Prize last month was awarded for measurements of stars and confirming that there is this supermassive black hole of a few million times the mass of the sun at the center of our galaxy. Yeah. And we think that essentially all galaxies at their heart, right at the center, have these supermassive black holes. Those are a million times the mass of the sun. We have a story where we can make these small black holes, like the one that LIGO and Virgo are seeing, at 10 or 50 times the mass of the sun. We don't really know how to make the ones that are millions, or even some of them are billions of times the mass of the sun. We don't know how to make those. We don't know how the universe creates those. It might start with these small ones and then just have a bunch of them collide and make bigger ones. Or it might start with a small one, and then you can imagine a galaxy kind of funneling a bunch of gas and dust and everything that the galaxy is made out of onto the black hole to have it grow. We're just not sure. Now, that's what makes this interesting, is maybe this is a clue of how to make this connection between this population of smaller ones and the population of supermassive ones. In between, we call them intermediate mass black holes, IMBHs. Yeah. And this object that we just detected is the first IMBH that we've detected in gravitational waves.
And so obviously we can get to the details of the physics. So between 50 and 120, some phenomenon makes it difficult to accomplish. But if I understand this correctly, Daniel, if you go beyond 120, 130, 140, then we can go wherever you want to go. It's just that gap that we are concerned about, 50 to 120? Okay.
Yeah, and I should say, I mean, this is, kind of a classic situation in science. The theory said there shouldn't be any objects there.
Yeah.
We detected this with LIGO and Virgo. And now, of course, there are lots of theory papers saying, well, if we change this, if we change that, if we assume black holes are made out of smaller black holes, there are lots of ways to create these sorts of things if you kind of are more creative.
Right.
And so there's a lot of activity now trying to be more creative. Now, I still think that there's these underlying physical processes, and we have hints that they really are there, because there's definitely something happening at around 40 to 50 solar masses where we can tell that there are many fewer black holes above 50 than below 50. So something is happening. but we're just at the beginning. We're trying to, figure out this story. The data is pushing us in certain directions, and then the theory needs to kind of account for it. And this is where all the fun happens, is trying to
Yeah.
sort all this out.
It's not a function of the sensitivity of the instrument, right? You're not necessarily looking in that range. It just happened to be. Let me ask you differently. So, are we finding a concentration of black holes in that range, 50 to 120, or we just found one or two?
Yeah, so we've only found one or two,
yeah.
but you asked exactly the right question, which is, do we have some sort of preference?
Yeah.
Are we agnostic or not? And the truth is, we actually have a preference for black holes in that range.
Hmm.
And so the fact that we've seen, say, 50 of these 50 binary black hole systems, and only a couple close to this range, says that there really are many fewer, because we're very sensitive to the ones that are bigger because we detect them farther away.
Yeah.
And so if there were the same numbers of big ones as little ones, we would be completely overwhelmed by the big ones.
Mm.
And we're not.
Right.
And so we know it's a smaller population, but we know there is a population. It's not zero.
Right. So that's what makes astrophysics so interesting, right? You have some theories and you do some experiments, you find something more interesting. Theory has to change.
Exactly.
And
go ahead. That's right. I mean, and you alluded to this before. I mean, I think as part of the story, what's remarkable is, the theory, if you start with general relativity and Einstein's theory from a century ago, it made predictions about there should be black holes and there should be gravitational waves. And that has been confirmed, really in an impressive fashion. I mean, at this point, there's no question these black holes really are they're crazy objects. They're very extreme, the most extreme objects in physics. And yet they exist. They're described by Einstein's theory. Everything seems to agree.
Right.
And so that's terrific. And it's a wonderful confirmation. But then there are all these details. How big are the black holes? How many of them are there? Do they occur in this gap? Can we account for how they're being made? Like, do we have a story that's consistent about how to make black holes?
Yeah.
That is really, right now, very unsettled. We have, to first approximate, we really don't know how these black holes are being made, at least some of them. And so that's what we need to figure out. And that's what the data will help us solve.
Right. Yeah. You even got the Europeans excited, Daniel. So I want to conclude with the next mission. I guess it's called LISA. It's 10, 15 years away. But that is sort of a different frequency, and it's going to be from space.
Yeah, that's right. So this is the Laser Interferometer Space Antenna, LISA. And it's the same idea. You're still kind of shooting light down arms and kind of measuring changes in distance. But now you're doing it in space. The problem is that the Earth is always shaking. There's, literally, and we talked about these little earthquakes, and that is happening all the time. And if you want to measure sensitively really big black holes, it turns out the Earth is shaking too much, and you can't measure them. So if you're interested in supermassive black holes, you can't build something on Earth to be sensitive to those. So you have to go to space, and LISA is that mission. And so it's 3 satellites, and lasers will shoot between them. And then that will be sensitive to these supermassive black holes colliding essentially throughout the universe. So that's an extremely exciting, mission. It's something that's been proposed and worked on for decades, and the Europeans are now leading it, and they're planning to launch in 2034, which, is still a ways away, but is close enough that the community is starting to get very excited about it. And the science that we will learn from that, should be tremendous.
Yeah, so the 3 satellites, are they sort of conventional satellites like geostationary orbits, or are they doing something very different?
No, they're doing something very different.
Yeah.
So they're in orbit. They're in an Earth trailing orbit. So they're in an orbit like the Earth going around the sun. But so they're not going around the Earth. They're actually going around the sun. And then they're in a configuration where they kind of orbit a common center. And so it's as if the three satellites are kind of rolling around in a circle around the sun. So it's a very specific configuration, which allows them to be sensitive to gravitational waves from all different directions. And it makes it particularly powerful for kind of teasing out the science we want to know about supermassive black hole collisions.
And they're adjacent to the Earth only for communication purposes. If they are actually revolving around the sun, the Earth doesn't really matter, right?
Yeah, that's right. And in fact, you kind of want to get away from the Earth because you don't want to have interference with the satellites. But yes, we need the data to make it to Earth.
Right,
so we need a specific configuration to make that all work.
Right. And so you will get a whole spectrum of data when LIGO comes back online with higher sensitivity. You are still sort of focused on that range, right? The 10 to 100 hertz to 1 kilohertz range, right? It's just a higher sensitivity, whereas LISA would be a different frequency.
That's right. So there, you're talking about something like millihertz or up to maybe decihertz. So it's instead of being sensitive to things which are orbiting each other a few thousand times a second, now you're sensitive to things which are orbiting each other. Maybe it takes 1,000 seconds or 100 seconds to go all the way around.
Right.
And that corresponds to much bigger black holes. So it's much lower frequency than is probed by LIGO. Right. And so it opens up a whole, if you like, a whole new window. One way to think about it is, if you've only been able to look through optical telescopes, so you look at your, with your eyes or your small backyard telescopes, and now suddenly you're measuring the universe in radio waves and using the giant radio antennas like Arecibo, the ones that you see in the movie Contact, those sorts of big antennas.
Yeah.
That's the transition we would be doing, but now in gravitational waves.
Are the expectation of the numbers lower as you go up in mass of the black hole?
Yeah, so this is something we don't really know.
Yeah.
We're not sure, but yes, the rough expectation is this is probably not something that will be happening, every few minutes in the universe.
Yeah.
It's probably more seldom. However, because we're at low frequency, we actually detect them for longer. So in LIGO, when we get a binary collision, we get, the last second. Right. Or, in the case of really small ones like the binary neutron stars, it's maybe a minute or a couple of minutes. And that's all we get. We get the very end of the collision. With LISA, we can detect things for, say, months. And so, that helps us because we can have many sources and we can be kind of observing them and watching them slowly spiral in. And that's kind of a different way to learn about the gravitational waves and the sources themselves.
Yeah. So the reason for that, Daniel, if I understand this correctly, is it because it takes longer for the bigger ones to actually merge, so they'll be dancing around a lot longer, and when they start off, they're creating sufficient amount of gravitational waves, but they're not moving that fast. Is that the way to think about it?
Yeah, that's right. So you can think of it as you go to bigger black holes, the whole movie slows down.
Yeah.
So every part of the movie is now slower. At any point, if you ask how long is it going to take to merge, everything kind of takes longer.
Right. Excellent. Yeah. So in conclusion, one more question, Daniel. So there is a whole field emerging here, which is really understanding gravitational waves. Will this help us in any way in, the other nagging questions around dark matter or anything like that?
So I hope so. I mean, there are a lot of big questions like the dark matter and the dark energy and what these things are. And one of the things I personally am most excited about is is trying to use gravitational wave sources to learn about dark energy and measure properties of the universe. And so that's something that I personally have spent a lot of my career focusing on, which is what I call standard sirens, which is just a way to probe how fast the universe is expanding by using gravitational wave sources. And where we have shown with this event, GW 170817, which was this binary neutron star event, which we detected in 2017, that was a very exciting event. And we could use that to make a first measurement of how fast the universe is expanding. It wasn't a great measurement. We have much better measurements of the rate of expansion by using supernovae or using the cosmic microwave background. There are other ways to measure this, but it was a completely unique way to measure this. And I think as we go forward, as we get more gravitational wave data, we'll start to really improve this. And so my hope is down the road, yes, I mean, the gravitational waves, everything we learn by measuring gravitational waves will help, shed some sort of light on, as it were, shed information. It's a new way to probe the universe. And maybe it'll help us figure out what this dark matter and dark energy really are.
Yeah, that'll be fantastic. My understanding is that the cosmological constant, there is a little bit of a disagreement with the current measurements, right? So if this comes sort of in the middle, that will resolve that problem.
That's right. So yes, right now it's very there's some very heated debates. So it's some groups say we use this number called the Hubble constant, and some groups say the Hubble constant is 72, and other groups say no, it's 67 kilometers per second per megaparsec. It's kind of this arbitrary unit, but that is a big difference in where we are now in precision cosmology. And so, maybe we'll come out right in the middle. Maybe we'll favor one group or the other. Maybe we'll end up somewhere entirely different. No matter what, it'll be fascinating. And so that's my dream is that we'll get to a point where we say, here's what we think the number is. And then, all the rest of the cosmological community can then respond to that, and hopefully it'll be exciting and help kind of inform what's really going on. We're not there yet, but I think we're definitely on the way.
Excellent. Yeah, this has been great, Daniel. Thanks so much for spending time with me, and good luck with this research.
Yeah, thanks so much, Gil. I've really enjoyed the conversation.
Thank you. Bye. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.